Okay. First, some announcements. So number one, there is a homework due tonight. It's not this group, so I can't. I've gotten emails about not knowing there was a quiz or not knowing there was a homework, but for the most part, every Tuesday, unless I say there's been homework, and every Thursday, unless I say there's been a quiz. Now, that is true, except for the week after spring break. Basically, Thursday you have a test, but then you haven't, I'm not assigning anything. So you cannot think about fundamental chemistry during spring break. You don't have a homework due. You don't have a test coming up. I did this on purpose so that you cannot think about fundamental chemistry for a whole week plus, and you can let your brains rest a little bit. So now there is one other announcement before I get into the thing, and that, well, today I have an appointment during our regular office hours, so I'm scheduling office hours from noon to 1:30 if anybody needs me, so that I can make up for the fact that there will not be office hours at the normal time. Okay, so on Thursday when you get here, there will be no, I said Dr. Evelyn. Our stockroom supervisor is going to be proctoring the exam. I will already be at a conference by that time. And so, just so that you have the instructions that I gave her, number one, pen, pencil, calculator, highlighters, drink, those are acceptable on your desk, but everything else should be put away and under the desk. Cell phone should be off or on silent. As per normal, you will only have 75 minutes to complete the exam because there's another class coming in at 9:25 that is taking an exam as well. So there's that. Basically, if you do things like normal, you're good. So, what's going to be on the exam? There's a question with 5 parts where you have to tell me how many significant digits are in a number. There's a question with 3 parts where I give you a number in regular notation, and you have to put it in scientific notation, and yes, significant digits matter. There is a question with 3 parts where I give you a number in scientific notation, and you have to convert it to normal notation, and yes, significant digits matter. There is a question with 2 parts. One is going to be a straightforward calculation. The other one is going to be one of the mixed operations calculations, where you have to do the math and record the number to the correct sig figs. There is a question with 3 parts where you have to round values to a specific number of significant digits. There is a question with 3 parts where you have to perform metric prefix operations. One will be very basic, one will have more than one step, and one will have cubic root or square root. There is one question where you have to read an answer to the correct number of significant digits. Oh, and on the metric prefix conversions, sig figs do matter. And lastly, there is one question with 8 parts, 4 formulas of acids that you have to give me the name, 4 names of acids where you have to give me the formula. That is exam 3. Any questions? The thing I'm passing out right now is a flow chart that will start to help, that will really start, we will start using a little bit today, but we'll primarily use it starting the week after spring break. Any questions before I get started into the material for today? Okay. So we began the semester through really exam number 1, learning about the atoms of the elements and the arrangement of the periodic table and that information. One of the things that we learned
is how to calculate the average atomic mass, which is the number that appears at the bottom of the of each square on the periodic table. If you'll recall, that average atomic mass is the result of taking into account all naturally occurring isotopes and their abundances. We then broke away and talked about taking these elements and forming compounds. And so exam 2 was about compounds. Specifically, it focused on how to name those compounds and how to get to the formula of those compounds. With a little of that extending over into exam 3. Exam 3 really is focusing more on the mathematics, specifically the fact that when we perform mathematics in chemistry, we should be focused on significant digits. And so all of our answers should always be recorded to the correct number of significant digits. Now what we're going to do is we're going to start combining the mathematics with the chemistry. And the first thing we are going to discuss is the difference between formula mass and molar mass. And then the other thing we are going to start doing is we're going to start doing dimensional analysis. Using molar mass and Avogadro's number. In this discussion, another piece that we'll talk about is we're also going to talk about mole-to-mole ratios. In formulas. Okay, so let's just take a moment and go back to what we know. And in so doing, I'm going to introduce this concept of formula mass compared to molar mass. When we look at the periodic table, if I look at aluminum, aluminum has an average atomic mass equal to 26.98 AMU. This is for 1 atom of aluminum. This would be aluminum's formula mass. Now, here's the problem with talking about aluminum in this fashion. And that is, again, we're only talking about 1 atom. We cannot manipulate 1 atom. We can't go upstairs into the laboratories and measure out 1 atom. We don't have the tools to do so. So this particular definition, the formula mass, is really not
a useful definition for us, or a useful tool for us.
So an individual by the name of Avogadro said, okay, now he discovered this using carbon, but we have since been able to apply it to any atom. Instead of one atom, we take 6.022 times 10 to the 23rd atoms of aluminum. Then what we're talking about is we're talking about this 26.98 in terms of grams. And that is something we can measure. We can go upstairs and measure grams using balances. Now, 6.022 times 10 to the 23rd of anything, which I'm going to just represent with a X, is equal to 1 mole of X. So when we talk about 26.98 grams, that is equivalent to 1 mole of aluminum. And this is referred to as aluminum's molar mass. Now, if you know anything about scientific notation, 6.022 times 10 to the 23rd of something is hard to imagine. I mean, that's, if you write it out, huge, huge number. So let me give you a picture of what 6.022 times 10 to the 23rd is. Again, 6.022 times 10 to the 23rd of anything is equal to 1 mole of that thing. If I take 1 mole of marbles, which I can visibly hold, I would have to stack the entire mainland United States 70 feet high of marbles. If I talk 1 mole of peas, I would have to cover every planet and a couple of Saturn's moons in order to get a whole mole of peas with 1 layer of peas. So yes, it's a huge number, but when we talk about an atom of aluminum, we're talking about something so tiny. That 6.022 times 10 to the 23rd is something you physically get and hold. Water. We talk about 6.022 times 10 to the 23rd water molecules. That is something that will fit into 18 milliliters, roughly. It's something that can be measured because, again, when we start talking about these aluminum atoms and these water molecules, they're so small that you can't possibly manipulate one because we don't have any tools that will allow us to go 1, 2, 3, 4. We don't have that type of tool. But we can get to 6.022 times 10 to the 23rd. So, now, this is one definition or one equality that we are going to use a lot. Because basically what we're doing is we're taking the microscopic world, which you have to have a pretty high power microscope, and we're putting it into the macroscopic world. Now, with this whole idea of molar mass and formula mass, we can also talk about molecules. Now, before we get into formula mass and molar mass of a molecule, you have to realize that chemistry follows the law of mass conservation. Basically, mass cannot be created nor destroyed. What it means for us is that each element, or each atom of an element, brings its mass with it in the formation of a molecule. So earlier, I was talking about water. Water's formula is H2O. That means that water has 2 hydrogens and it has 1 oxygen. Now, hydrogen, according to the periodic table, has a mass of 1.01. And oxygen has a mass of 16. Each of these hydrogens has to carry its mass with it. So in other words, that is 2.02 atomic mass units that are brought when the hydrogens are added to the water molecule. And the oxygen brings 16.00 atomic mass units. So the mass of water is 18.02 AMU. Now, that 18.02 AMU is associated with 1 molecule of water. And again, this would be termed its formula mass, because it is the mass associated with 1 formula unit. Now, I've already said this, we can't manipulate one water molecule. So we can do the same thing with water as we did with aluminum. A water molecule has 2 moles of hydrogen and it has 1 mole of oxygen. The hydrogen has a mass of 1.01 grams. the oxygen a mass of 16.00 grams, meaning that the hydrogens carry 2.02 grams to the overall structure, and the oxygens carry 16.00 grams, meaning that it is 18.02 grams. That is 18.02 grams is equal to 1 of water, is equal to 1 mole of water. And just like we said before, that means that we're talking about 6.022 times 10 to the 23rd water molecules. This would be its molar mass. The term molar mass coming from the fact that you have moles, molar, and you have the unit of mass, grams, so that's its mass. That's where it comes from. So basically what I'm trying to say is there's no difference between how you calculate the formula mass and how you calculate the molar mass. The difference is in the units. When we're talking about a formula, we're talking atomic mass units, which is what we calculated when we determined the average atomic mass. And we're talking about only one of that substance. Whereas when you're talking about the molar mass, you're talking about 6.022 times 10 to the 23rd of that substance. And therefore the units are grams per mole. But there's no difference in how to calculate it. There's no difference in the numerical values. The difference comes in the units. So let's look at another example, and we'll get formula mass and molar mass. Let's look at aluminum hydroxide. Now, you have to remember what that parentheses subscript means. What it means is you have aluminum and you have 3 OH units. That's what that subscript means. So when we start to calculate this, we have 1 aluminum, we have 3 oxygens, and we have 3 hydrogens. Now, folks, you don't have to write this out unless you just need it to understand what we're dealing with. It's simplest to just take that subscript and multiply it by the subscript inside the parentheses. So 3 times 1, 3 times 1. But if you need the visual, then that's why I wrote it out this way, because what this is indicating is you have 3 hydroxide units. Now, aluminum is again 26.98 AMU. Oxygen is 16.00 AMU. And hydrogen is 1.01 AMU. The aluminum contributes 26.98 to the overall structure. The oxygens contribute 48.00 to the overall structure. And the hydrogens contribute 3.03 to the overall structure. When added together, you get a mass of 78.01 AMU. That 78.01 AMU is for one aluminum hydroxide molecule. And it would be its formula mass. Now, again, we can calculate the molar mass. We have 1 mole of aluminum times 26.98 grams. We have 3 moles of oxygen times 16.00 grams. And we have 3 moles of hydrogen times 1.01 grams. Therefore, we're looking at 26.98 grams being contributed by the aluminum, 48.00 grams being contributed by the oxygen, and 3.03 grams being contributed by the hydrogen, for a total of 78.01 grams. Again, that's 78.01 grams of aluminum hydroxide is equal to 1 mole of aluminum hydroxide. In this case, we're talking about 6.022 times 10 to the 23rd aluminum hydroxide molecules. And it is its molar mass. I want to do one more. And I am going to calculate the molar mass. Of calcium phosphate. This is more how you're going to see it written on an exam. You will also have a question related to what is the difference between a formula mass and a molar mass. But calculations, typically we're going to go straight to the molar mass. We don't really calculate formula mass that often, simply because it's for one molecule, and therefore it's not a very useful value for us. Okay, so in this case, we have 3 moles of calcium. We have 2 moles of phosphorus, and we have 8 moles of oxygen. Again, to get the calcium straightforward because it's 3, but to get your phosphorus, you multiply 2 times 1. And for the oxygen, you multiply 2 times 4. Now, calcium has a mass of 40.08 grams. Phosphorus has a mass of 30.97 grams, and oxygen a mass of 16.00 grams. The calciums contribute 120.24 to the overall structure. The phosphoruses contributes 61.94, and the oxygens 128. Now, when we're doing significant digits, the moles do not count. Those are exact numbers. You can't have a half of an atom. So when we deal with this, the mole portion is not counting. So the number that is counting is that 40.08. That has 4 significant digits. So if I were to record this correctly, it would be 120.24, where the 4 is not significant. So that there's 4 significant figures. For the phosphorus, it would be 61. Let me make sure that looks right. 61.94. And for the oxygen, it would be 128.00. Now, when you add them together, you get 310.18. So if I were to record this, it would be 310.2 grams of calcium phosphate is equal to 1 mole of calcium phosphate. And the reason for that is because due to that, you always, when you're adding, it is always based off of the one with the fewest decimals. The one with the fewest decimals only had 1 decimal, and that's why our answer ultimately can only have 1 decimal. Now, I will warn you, when it comes to, when we get into other calculations besides just the molar mass, I usually keep all digits, because the molar mass is usually not the defining quantity. And the reason I usually keep all digits is because it really is dependent upon what periodic table I use. The one over here, instead of 16.004 oxygen, has it as 15.9994. That has a lot more significant digits already. The calcium is 40.078. So the reason, so on a test, yes, if all I do is ask you for the molar mass, pay attention to C6. But if I'm asking you to calculate something else, the significant digits in the molar mass are going to usually be much larger than anything else, because it is dependent upon which periodic table you use. Any questions about the how? So 2 things. Number 1, Any questions about what the difference is between a formula mass and a molar mass? Question number 2. Any questions about how to calculate formula mass or molar mass? I mean, relatively speaking, I feel like this is one of the easiest things we've done. But, you know, I want to double check. Because I believe, though I can't remember for certain, this is one of the key things about the homework tonight. Is can you calculate formula mass and molar mass?
Why is that 4 on 120.249?
Because this only had 4 significant digits. So this could only have 4 significant digits. Because it was multiplication division.
Yeah.
Other questions?
But you have to do it like that, or you put it as below, you can't just leave it off.
If I would have left it off, my rounding would have been off. I would have had a rounding error. So it's always best to not do any rounding until you get to the very end, so that you don't have a compound error, is what it would be considered. That's why I always subscript my insignificant digits, is so that I don't wind up with a compounding error. Other questions? I like questions. This class is always so quiet. Oops. Okay. So the next thing we're going to talk about is mole to mole ratios. Which you will see me abbreviate as MOL:MOL, found in the formula of a compound. I've already indicated these multiple ratios by how I've written the information. When I look at calcium phosphate, if I have 1 mole of calcium phosphate, how many moles of calcium was there? Well, there were 3. So in other words, the ratio is 1 mole of calcium phosphate to 3 moles of calcium. I can continue and say that for 1 mole of calcium phosphate, there were 2 moles of phosphorus. And for 1 mole of calcium phosphate, there was 8 moles of oxygen. That's all I mean by a mole-to-mole ratio of the atoms to the overall formula. Is you literally are, I mean, you do this every time you calculate the formula mass. Excuse me, back up, rewind. You do this every time you calculate the molar mass. Because every time you calculate the molar mass, you pull out from the formula the number of moles of that element. Every time you calculate the molar mass, you pull out the number of moles of that element. And once you're done calculating the molar mass, that mass is set equal to 1 mole of that compound. So therefore, 1 mole of that compound had to contain 3 moles of calcium. 1 mole of that compound had to contain 2 moles of phosphorus. So we did this, we just didn't specify it as a mole-to-mole ratio until just now, where we said, okay, for every calcium phosphate, there is 3 moles of calcium. That's all there is to a mole-to-mole ratio of an element in a compound. So, let's talk about the things that we have developed. So far, without realizing it, we have come across 3 conversion factors used in dimensional analysis. The first conversion factor is Avogadro's number. Which is 1 mole of anything is equal to 6.022 times 10 to the 23rd of that thing. You will use Avogadro's number anytime you're working with atom. Anytime you see the word atom, ion, or molecule in the question. The second conversion factor that we have developed is a molar mass, which has the unit of grams is equal to 1 mole. I guess we'll put it as y grams. I don't know, z grams, but grams per mole. This is going to be used anytime you see grams in the question. The last conversion factor that we have developed is a mole-to-mole ratio. The units are mole to mole of two different compounds. And you'll use this anytime you need to convert between two unique formulas. So this sheet I passed out. This sheet is divided into A and B. Here, A represents a particular formula like calcium phosphate. B represents a particular formula like just oxygen, O. They are two unique formulas because Ca3PO42 does not have the same formula as just O. So even though oxygen was an element in calcium phosphate's formula and oxygen's formula are different. So that's why you have A and B. Don't worry about the bottom third of this sheet. You mainly need the top 2/3. Now you will notice anytime I started with grams, my conversion factor, which is the conversion factors are listed on the arrow. Anytime I started with grams, I used the molar mass to get to moles. That is true no matter whether I was talking about A or whether I was talking about B. The conversion factor from grams to moles is molar mass. And you'll notice at the top, I said atoms, ions, or molecules of A. And every time I said atoms, ions, or molecules of A, I went to moles of A using the Avogadro's number. That is true no matter whether it's A or whether it's B. What I'm trying to get at by showing you this is we can have a conversion that has 3 conversion factors, but the only conversion factors we are using are these right up here. So let's look at some examples. And let's learn how to, so when we, let me first dimensional analysis is, first of all, before I get into a problem, the process for dimensional analysis is the same process you used for the metric prefix conversions. Meaning you identify what was given to you. You identify what you want to solve for. You determine possible conversion factors. You'll then do the calculation. And in the calculation, we will always be making sure that the conversion factors cancel out as we move from left to right in the calculation. So let's look at an example. How many chlorine atoms are in 24.96 moles of calcium? What in the heck did you do to me? Cl subscript 2. Calcium chloride. Okay. So what were we given? We were given 24.96 moles of calcium chloride. What were we asked to solve for? We were asked to solve for chlorine atoms. Now, what I'm going to do is teach you how to break this down. First thing, calcium chloride and chlorine have different formulas. So, because they have different formulas, I am going to need a mole to mole ratio. The mole to mole ratio will come from the chemical formula. So for 1 mole of calcium chloride, there are 2 moles of chlorine. The next thing I notice is that I need moles of calcium chloride, and I have moles of calcium chloride. So I am good there. But the last thing I notice is that I need atoms of chlorine. Because I am dealing with atoms, that means I'm going to need Avogadro's number. Which is 6.022 times 10 to the 23rd of anything, in this case, chlorine atoms, is equal to 1 mole of that thing. 1 mole of chlorine. From the question, these are the 2 conversion factors I could determine. So now I'm ready to do the math. I'm going to take 24.96 moles of calcium chloride. My first conversion factor is going to need moles of calcium chloride, so I'm going to use the mole to mole ratio. The mole of calcium chloride will go in the denominator so that the mole of calcium chloride will cancel out. The moles of chlorine will go in the numerator. And that uses up your mole to mole ratio. But I didn't ask for moles of chlorine, I asked for chlorine atoms. So that's where I've got to use Avogadro's number. The 1 mole of chlorine from Avogadro's number will go in the denominator so that the unit and the substance cancels, leaving me 6.022 times 10 to the 23rd chlorine atoms for the numerator. I was asked for chlorine atoms, so I am now ready to solve this calculation. 24.96 times 2 times, what in the heck are you doing? 6.022 times 10 to the 23rd, and you get a value of 3.006 times 10 to the 23rd chlorine at, or excuse me, 25th, 10 to the 25th chlorine atoms. Now, we need to pay attention to significant digits. Our first value had 4 significant digits. Mole to mole ratios are exact numbers, so they have an unlimited number of significant digits. 6.022 times 10 to the 23rd is a number in scientific notation, so all the sig figs are in the mantissa, so there's 4 sig figs. And when we're talking about the mole portion of the Avogadro's number, it is unlimited, so it has an unlimited number of sig figs. This is multiplication and division, so the answer will have the same number of significant digits as the measurement with the fewest. The measurement with the fewest had 4, so our answer should have 4, and therefore 3.006 times 10 to the 25th is what we should record. Because now molar mass and mole to mole ratio, I feel like hopefully you'll remember going into coming back from spring break, but because dimensional analysis is going to be something that we're going to do, I think I'm going to wait and do more problems when we get back from spring break. And that way I can do a couple more problems, 2 or 3 more problems of this nature, and then we'll get into balancing chemical reactions. Questions for me? So again, your test is on Thursday. The individual that will be proctoring the exam is Rebecca Rodriguez Palacio. Though you don't, I mean, you may not need to know that, but that's going to be who will be here. I am planning on picking up the exam on my way back through from the airport. So I'm hoping that I get it graded by the following Tuesday after spring break, but it will not be graded until that weekend, the last weekend of spring break. So I normally have your test grades back pretty quick, but because I will be out of town, they won't be back until the weekend after spring break. So at the earliest. So don't even panic, because it's not that I haven't, it's just I won't be able to grade them till then. Any questions for me? Today I'll be in my office from noon to 1:30. I can't do my normal office hours, so. And like I said, this last piece, I've introduced it, but don't worry about it. We'll pick it up after spring break. I will answer questions in the last 8 minutes about, if you have questions about the test.